welcome back. Now we're going to be talking about section 7.5, which just kind of takes everything and puts it together, right? So what we mean by that is to say, you know, I'm never going to just be in a situation where, you know, I might have some sort of problem to work out, right? So involving integrals, and you're going to get one. They're always going to tell you this is exactly the method you're supposed to use, right? Because it doesn't work like that. Sometimes the method to use may not be the most obvious thing, or you may not be told, so you have to really think about what you're given to understand what method might be the easiest, right? So what I have written here is a list of all of the integrals that we know, kind of our basic integral identities. If you don't remember, you know, maybe there's a few in here that you don't necessarily like have to memorize. Like maybe we could always get back to this one or back to the just missing in some way, or even we could use like on these ones that are the sine inverse and the tan inverse. We could actually use trig substitution to find this as well if you forget. But it does kind of help to have a neat little chart that has kind of all of our basic ones in it, so we know that, oh, this looks like this example, then I could probably make an easy substitution to make it work, right? And so what we're going to be doing for this class for the most part, I'm going to kind of like explain through this list a bit, but I kind of want to just go through 7.5 and look at the even problem. So we're just going to discuss what's the method to use on it, which one do we use, right? Which is going to be all that we use. This one, this one, this one, like how do we approach it, right? And so we're going to run through all those things. But the book does give kind of a nice list to at least start you off of thinking of where to go from, right? And the first step here says simplify, right? Now what this means, right, is, I mean, you might be given some sort of integral at some point, right? That's maybe, you know, you have this problem, right? And some of the first instinct of some people would be to say, oh, no, like that looks very difficult. How do I handle it, right? But these terms both have a what in them. They both have next to them. What's on the bottom? It's x, right? So you can just divide the x from both of these terms. So you get x squared over x, which is x, then you get x squared over x. These are the same thing. Right now, they might have, this one has like maybe one less value, right? Because I can't plug in 0, but otherwise it's the same function, right? But this is really easy at this point, right? So your goal first is to say, is there some way that I can make this simpler for myself? Can I write this easier? Okay? Right? Don't just take this and say, oh, I have to accept this integral work, because that's not always going to work out. Second thing, right, is do we have any obvious substitution, right? So, you know, I don't know, let's give an example of this. Let's say I had the integral of (2x sine of x squared), right? At first, you might say, oh, this is an x squared in there. This is a real problem, right? But there's a really easy substitution I can do on this, right? Which is what? What is u, a to b? X squared. And du is 2x dx, which is exactly what's outside, right? So then this is just simply the integral of sine of u du, which falls into the camp of our, you know, kind of our list, right? We know what that is, right? So I don't need to go through any of my crazier methods to do this, because I can just do a u substitution and make it work, okay? So the first two options are there just to say, don't always assume the hardest. Try to make it easier, okay? Good. The third, right, says to kind of classify, right? So it says classify the integrand in specific, which just is the thing on the inside, and we're supposed to answer what is it that I have on the inside? What am I doing with, right? And so the first question you might come to is, do I have a bunch of trig functions in it, right? Is it just sine, cosines, multiply together, tangent, secant? Is it just some combination of trig functions? Well, if that's the case, right, if I have something like, sine to the fourth x cosine cubed x, right, then I might want to consider using methods from 7.2, right, which is where I did the trig integration, right, because I have a bunch of trig functions together, and so maybe there's some sort of way that I can change this so that I can have this obvious substitution, right? So we have trig. Is it a rational function, right? We just talked about this one today. If I have a rational function, right, like this, where there's not some sort of simple substitution, right, that I can do for this, then my idea might be to try to do integration by parts to split this up, right? Or not, sorry, partial fractions to split this up, right? Where I can factor the bottom and say, okay, here's a over this thing, bx plus c over this thing, or b over this thing, whatever it is, right? To try to break it down, right? Just take that rational function and put it into its parts. Because right now I can't do a u sub, right? It's not going to work out. Oh, yeah, no, it's not going to work out. If it was a minus, it might work out actually. In this case, it's not going to work. So, but yeah, we would want to resort to something from 7.4, right? If I have radicals, right? So, and I'm not talking about that square root of x plus 4 thing, right? Because that's not really what I'm looking for. When we talk about radicals, right, we're thinking probably something like this, or something like this, right? If I have this in my problem, it's probably a good hint that maybe a trig substitution, or yeah, a trig substitution is going to work for this problem, right? Or in this case, right, I would want x to be, well, if I had this in my integral, we'll let x be in there. Okay, in that case, what do we think? If I have x squared plus 4. Three options. Either sine, tangent, or secant. It's tangent. In this case, it'd be 2 tangent, right? And that's just because I get 4 tangent squared theta plus 1, tangent squared plus 1 is secant squared. So then I can take a square root, right? So if I have this, right, if I have this radical in here, a good idea might be to try to use trig substitution because that's going to cancel out that radical and make it work, okay? Good. When I say transcendental, the functions that we're kind of thinking about here are something, I mean, kind of include sine and cosine, right? But also are going to include things like e and natural law, right? Now, if I'm taking any of these functions, right, and multiplying them by some polynomial, right? So if I take sine and I multiply by x, cosine and that's by x squared or something, e to the x times 3x, just 3x, right? ln times, well, no, ln times, I don't know, whatever, x to the 4th, right? That one is going to be a really easy case where I'm going to see, oh, I need to use some sort of integration by parts, right? Especially because, remember, if I have, I can't remember if we did this one in class at all, but if I have x e to the x, right, then if I let u be x and dv be e to the x, then what's going to happen is that x is going to become constant, right? So we get v is e to the x, and then from there, I'm left with x e to the x minus the integral e to the x times dx, because the x is gone, that becomes easy, right? So if I have one of these crazy functions multiplied by a polynomial, then probably integration by parts is going to be the way to go, right? So when we talk about transcendental, that's kind of what we're aiming for. Obviously, if I have like e times natural log or something, you might need to be a bit more wary of if that's going to work. But these are like the simpler cases, ones that popped up a lot in the integration by parts. Okay. So what if I went through step 1 and 2? I thought about all of these and I couldn't figure it out. There just wasn't anything that stuck out to me. Okay. Well, the book here just says try again, I guess. So just try again. Really try. Okay. Really think about it. Okay. Just think about, hey, is there some sort of special substitution? Right. Again, think back to just a bit ago. to that u is the square root of x plus 4 example, right? That worked out really nicely so that I could turn it into partial fractions. So then I could work it out, right? Now, it's not something you're going to think of off the top of your head, but obviously that's a case where I want to try something, right? I want to try to figure something out and work through it, okay? Parts, right? Obviously, if I don't have like this obvious parts case, I can still work things out, right? Like if I have e to the x times sine x, remember we had to like do the parts a couple times and add things over, but I could still work it out. Something very similar to what we did when we found secant cubed, whenever we did that integral. Sometimes you just need to take clever picks of your function and do integration by parts with it. Because it is a very powerful sort of method to kind of shift things around and work with it. So it's worth it to play around with it. Manipulate, what this means is if I have a function, and I think really the book is a kind of a great example of this. Let's see, it says, yeah, so it says, right, so it says, what if I have 1 over 1 minus cosine x inside my integral, right? And I'm like, okay, well, what do I do with that? I went through everything, I don't really see anything that works. Well, an idea to have, again, is like to kind of manipulate it, right? To take this fraction, or maybe take what I have, either to maybe rewrite it like I could sine and cosine, or take the top and bottom and multiply by something to have a pretty clever solution. In this case, what if I took the top and bottom of this and multiplied it by 1 plus cosine? Well, when I do that, I'm going to get the integral of 1 plus cosine x over, what's 1 minus cosine x times 1 plus cosine x? Okay. What's that going to be? 1 minus cosine squared x. See, there it is, right? It's going to be sine squared x on the bottom, actually, right? So that idea actually gave us this, which then we're going to have 1 over sine squared, which is cosecant squared, plus cosine x over sine squared x. Right, now notice, no cosecant squared, and this is a simple u sub in the obvious substitution section where we say u is sine, du is cosine, and that's going to be an integral we can do. Okay, so let's try to think about, if I have 1 minus cosine. If it was squared, it'd be sine. Could I make it squared? Oh, yes, good. And so we get that. Okay, so that's kind of what it means by manipulate. Past examples just says, this one looks hard, but I think we've talked about this in class, or I've seen it in the book done before, or I've done something similar on a homework before when they told me what to do, right? When they told me what method to do, right? And so that kind of sticks with you, and from there you can kind of go back and refer to it and say, I think this is a good educated guess. And then the last one I didn't write on there, but it just says, try all of the methods, right? Just really throw everything at the wall, see if anything kind of pops out to you, makes like works, right? And that's going to be kind of the way to do all this, okay? So after all of that, hopefully you get there. Now, there are unfortunately still some integrals that you can't do even with all of this, which you talk about how to do in 7.7 with approximate integration, but it's always worth it to try to pull out each of these methods to see if something works. Okay. Any questions on that discussion? Again, the best way to learn this is by example. So we're just going to talk through examples. Just kind of say, what should we do here? What do we think about this one, right? Because that's the ultimate best way. You can feel free to kind of like what the book kind of gives. This might be a good like, oh, I tested this, it didn't work. Let me test this, but this didn't work. Let me test this. Is a good kind of thought process there. Okay, fantastic. So let's do it. we're just gonna start with, we're not gonna evaluate them. Don't worry, we won't spend as much time doing the evaluation. Well, at least tell you how to start it, right, of course. But we're just gonna look at each of these problems and think with a critical eye of how to do it. Okay? So, number 2 is the integral, and it's a definite integral. But let's do an indefinite integral. So I'm given this. Okay, so we have this, the integral of 3x plus 1 to the square root of 2 dx. Okay, so is there any way that I can simplify this? Simplify this expression down at all? What do we think? Anything? No. Yes, there's no way to simplify this. Okay, and this is a square root of 2, by the way. Okay. Good. So next, is there an obvious substitution here? Right? Is there maybe an easy substitution that we could make? Yeah, so notice it's just a linear term in here, right? So this is an easy use of because we just let u be 3x plus 1. And so du is going to be, what's du in this case? 3 dx. So I'll write dx as du over 3. And so that's going to give us the integral of u to the square root of 2 times 1/3. Okay, so this 1/3 can come out, right? Do we know how to integrate u to the square root of 2? Yes, we do. This is just power rule, right? This is just an example of power rule, right? That's all that's going to happen. I just take, even though it's a weirder number to 2, it still is power rule, right? There's nothing, none of this other stuff yet. This is actually a problem we would have had in Cat 1. That's completely possible to do. Okay, so in this case, we can just do a u substitution, right? So I'll go kind of. Okay. Next one, number 4. Into the integral of sine x over cosine x. Okay. So, can I simplify this? I don't know. I mean, you could always maybe do sine over cosine. Say a tangent and times sine squared. Right. So that's, yeah. So that's going to be kind of our step, right? So we say there's no way to simplify. There's no obvious, right? Because I can't let u be cosine and get sine because it's sine cubed, and I can't let, at the moment at least, I can't let u be sine because the cosine is in the denominator, right? So the next question is, there's a bunch of trig functions here, right? So maybe I can use some of the like 7.2 section things to do this problem, which is absolutely going to work out actually. Again, you really need to practice and kind of think through these, but it's always worth it to experiment, right? So we have, if you refer to that section, remember that I kind of talked about if this thing's odd, then take out this one and write it in terms of cosine, or if cosine's odd, take one out, write everything in terms of sine, right? In this case, we do have an odd sign, so maybe it's a good idea, even though there's a cosine in the bottom, to rewrite this as sine x times sine squared x over cosine x. And then how can I rewrite sine squared? So what I'm going to do, I'm going to write that as 1 minus cosine squared over cosine, and then times sine x. Just go ahead and move that sign down. Right now, from here, I can actually make a decent use of, because I can just say u is what in this case? What is it? Cosine? Yeah, thank you. And du is going to be like that. And so we're just going to get the integral of 1 minus 2 squared over u du with this negative sign as well. And then from here, right, again, just like we talked about earlier with dividing the x's, I can just take this u, since there's only one thing on the bottom, and divide it from each. So I'm going to get 1 over u, which we know how to integrate, and minus u, which I know how to integrate as well. So from there it works out. Okay, but the ultimate idea there was there's a trig expansion that I can work out. Okay, because obviously there's, if you try to go any farther, there's no rational radicals, no polynomials or anything. So this, you know, maybe you could try some special substitution, but at the moment this might be the best bet to at least attempt. Okay, is that good there? Okay, let's keep going. So we're going to have, so number 6 is going to be the integral of x over 2x plus 1 third power. Okay, can I simplify this? Yes. Okay, right, because there's no easy division, no like something to square. I mean, I could cube this, but honestly, that might make it more complicated in this case. There's no obvious substitutions here. Again, maybe if you're thinking about a substitution relating this and this x, that would kind of be more in the special substitution area, so it might pull off on that. There's no trig functions. No, right? It is a rational function, though. Right? This is definitely a rational function. So we could try to do partial fractions on this, right? What would partial fractions look like in this case? If I tried it. What pieces is it going to break up into? Fantastic. From there, we use the methods. We learn to get these values, and then these, even if you don't know the constant, all these are actually easy to integrate. Because we did this one in Calc 2 just last week. This one you should know for Calc 1, and this one you should also know for Calc 1. Okay. Good. Let's keep going. We'll go until everybody's tired. No, we're going all night. Okay. I'm just kidding. Number 8. Gotta skip all the odds. Those are for you. And you have to work them out. You have to work them out for that time. Okay, don't just stop. Okay. At least in the extra homework. I will on the mandatory homework. Just have to name it. Okay. Number 8. The integral of t sine t cosine t dt. Interesting. Okay. We're just going to run through it in our mind again. Okay. Is there any way I can simplify this? No easy. You could. There is, right. We do have a trig identity. Right, maybe I'll give this as a suggestion if you want to try it out. We do have a trig identity where you can write that relates sine t and cosine t together by multiplying them, and that's sine 2t, right? So you could technically rewrite this in terms of that, but for now, maybe I'll pass on doing that way. But you can absolutely do that. Okay, let's say you forgot that identity for some reason over here, right? Which is okay because we have other ways to do this, right? So no, is there any obvious substitution here? Come on, guys, it's obvious. There's obviously it's sine t, right? Because then you get du is cosine t. Oh, yeah, that's right. Yeah. Yep, can't forget about the t. The t there messes everything up. So there's no obvious substitution here. There are trig functions, but there's also a t here, again, which causes issues. It's not a rational function. There's no radical. But it does kind of fall into that category where I have, even though I have two trig functions, it is still like a polynomial times a trig function, right? So maybe let's take this and we'll apply integration by parts to it, right? Right. The first guess is to say u is t, right? Because if I take the derivative of t, that would give me dt, that would go away. So what does that leave dv? So what's du? 1, right? Which 1 dt. Don't forget about the dt's there. V, okay. Now without that t there, can I integrate that now?
Yeah.
Absolutely. I could let u be sine, du be cosine. And so you can work that out. It does end up being 1/2 sine squared t in that case, or negative 1/2 cosine squared t, depending on which way you're working out, but they're the same. Okay, and then from here, I would have u times v, right? 1/2 t sine squared t minus the integral of v, which is sine squared t. Right? Now, it's still not maybe the easiest thing, but I do know how to integrate this still, right? Because we learned it from 7.2, right? How can I rewrite sine squared t? What is it?
2 times sine.
Not sine 2t, sine squared t. There's a difference. 1 minus cosine 2t over 2. So I'll put that in there and then I didn't hear that. Okay. What sine 2t
is 2 sine t cosine t.
Yes. This is sine squared t. Right? Don't get those two confused. Right? This is 2 times the angle, and then this is the sine of each squared. Okay. Good. And then you work that up. Okay. Yeah, kind of maybe clicking a little bit. Okay. Really just trying to associate each one with something. Okay. So now we'll do number 10. Number 10 says we have cosine of 1 over x cubed. Oh, interesting. So we can't simplify this. Yeah, so absolutely. There's kind of an obvious substitution here, not really, because right, I could say u is 1 over x, correct? Right? And so what would du be in that case? Yeah, it's negative 1 over x squared, but yeah. X, right? And I almost have that, right? Instead of x squared, though, I have x cubed, right?
And then you can just take out the
Yeah, absolutely, right? The last, I have 3x down here, so 2 of them will go to the du, but then the other one is going to be u. And let me write that explicitly so you can kind of see it. So this is the same thing, right, as the integral of 1 over x times the cosine of 1 over x times 1 over x squared dx. You kind of see that here where I have, if I let u be 1 over x, then this 1 over x can be u as well, and then this can all be sucked up into the du, giving us minus, because that minus comes from here, the integral u cosine u du, which then this is a very easy integration by parts at this point, right? Now, again, you may not have come to that conclusion from obvious substitutions, which is that's okay, right? You can still run through trig, no, rational, no, radicals, no, transcendental. Kind of, it's not really quite in the form we wanted. But then, maybe that brings you to that special substitution category, right? Where you say, maybe let's really think about that substitution because it really looks like it could work, but it's just so close. And it is very close. I just have to do this u substitution. You would have encountered an example like this in Triple at some point, but this is obviously a bit more on the extreme, not extreme, maybe sometimes less obvious, but again, we want to train our brains to think through that, but we can do this. Okay. Cool. Any questions up to this point? We've done 5 so far. I'll probably still have to. We'll probably end early. This is the integral. It will have like a like 2x minus 3 over x cubed plus 3x. This is almost like the one I wrote. Oops. Okay. Can I simplify this? I mean, what is it? Partial. Yeah, so we could end up using partial fractions here, right? Absolutely. I mean, it looks just like a partial fractions problem, right? So in that case, it's like, oh, that's first. But a simple u sub isn't going to work here. We can't simplify it, and there's no trig, so that kind of just leads us to the next step. But this is a really easy setup for partial fractions, even though it does have a irreducible polynomial once you factor it, right? Because the bottom is x times x squared plus 3, so you have to worry about that. But otherwise, it's just a kind of a key example of partial fractions. Okay. Number 12. Or I just did number 12. Number 14 is going to be the integral of the natural log of 1 plus x squared dx. That's interesting. So we can't simplify it. There is definitely no obvious substitution here. There's no trig, not a rational, no radicals. We do have a transcendental function involved, but there's no, it's not like a simple, there's no obvious selection here, I guess is the point I want to make. But, what is it? That sounds like a good idea. Yeah, absolutely. So again, maybe that kind of falls into our part range now, right? Because we don't really have a neat special substitution I could do here. At least I can't, we can't think of one at the moment. But maybe parse words, right? Let's let u be the natural log of 1 plus x squared, right? Do you remember when we did natural log of x, just the integral natural log of x, we let that be our u, and it really worked out nicely? Maybe we'll get something here. So u is natural log of 1 plus x squared, dv is just dx, because that's all it's left. So what is du? What is it? 2x. Not 2x. It would be 2x if it was just 1 plus x squared, but it's the natural log of 1 plus x squared. So what are we going to get? X over 1 plus x squared dx, and then what's the integral b? Awesome. So absolutely. So then this integral becomes u times b, get x times the natural log of 1 plus x squared minus the integral of v times. Now, this still doesn't look quite where you may want it to be, but let's think about this guy for a sec, right? This is going to be 2x squared over 1 plus x squared. Maybe using our partial fractions brain, we can say, well, let me divide that x squared and this x squared from each other and see what happens. Right? So maybe I'll compare. Let's do it real fast. If I take 2x squared and I divide it by 1 plus x squared, or maybe I'll put it around x squared as well. How many times does x squared go into 2x squared? Twice. Yep. So I'm going to subtract minus 2x squared and minus 2. So minus 2. So this integral is the same thing as the integral of 2 minus 2 over 1 plus x squared. Oh, quiz, do I know how to integrate this one? Yes, we do, actually. This is not natural log. It would be natural log. It's, what is it? It's tan inverse. Yeah, now I have a special format for tan inverse. You could just where a is 1, right, in this case, but it's absolutely, it's just tan inverse. Which if you didn't remember, you can always use trig substitution, but it does help if you do remember it, right? Yeah, okay. Let's see. What have we, so we've gotten parts problem, we've gotten a trig problem, we've gotten a partial fractions problem, we've got just a simple use of. Maybe we'll go one more. We'll call it here. Okay, number 16. We have the integral from 0 to root 2 over 2 of, and again, I wrote the bounds in there, but I'm not. X squared over the square root of 1 minus x squared dx. Okay, so we could run through the list. Can't simplify. No obvious substitutions because I have an x squared on top. It's no trig. It's not a rational function, but there's a radical. How about that? Right. This one should automatically, if you've been spending some time with the trig subsection, this one should automatically make you just think about trig substitution, right? So what would be my trig sub in this case? What is it? So we're going to do sine theta, and then dx would be cosine theta. And we would plug that in, right? So again, I'll just ignore the bounds for now. But we get sine squared over the square root of 1 minus sine squared, which is cosine squared, cosine theta. And then these would cancel, which you'd actually get sine squared. And if you were doing all even problems, you would have done that one already earlier. So maybe that's another one to memorize as well. But that makes sense, right? Now, once I do get the integral, right? Is it okay to leave it as just the integral, like as in terms of theta? I need to change it back, right? And when we do that, we need to use our triangle to do that. Okay? Because I know sine theta is x, which means x is the opposite side, 1 is the hypotenuse. And from there, we get okay. Let's do one. And that'll be it. Okay. This is the hardest one of all, right here. Can I simplify this? No. Is there an obvious substitution here?
Yes.
Yes, there is actually. Absolutely. What is it? Maybe 1/2 t to the negative 1/2, right? dt, which is 1 over 2 root x. So we're missing the 2. right? But it's just a constant, so I can easily work with that. So I get 2 du is 1 x dx, and so this is going to turn into the integral, 2 times the integral of e to the u to u. And what's the integral of e to the u? So we get 2 du plus c, which is just 2 e to the root x. There's the first one actually. Let's see, because it doesn't take very long. Okay, so again, some of them might be a bit more complicated, but some of them will be really easy, right? It's all a game of, really think about the problem and make sure you know what you're doing. Don't make the hard ones easy and don't make the easy ones hard. Okay, just make sure you really have a thought process that decides what's best here, what's going to work here. How do I play this together? Okay, and as always, like practice the other sections, 7.1 through 7.4. Couple things I want to say before we leave. One, 7.7 is uploaded. I haven't done 7.8 yet, and I do have to work on this, so I'm not sure when I'm going to get that. So I have the homework due Saturday, but I think since I just behind on recording that, if you could just pass by 7.8 for now, at least do 7.7. All I ask you to do is watch one video. That's okay. And then we can I'll try to mention like 7.8. Maybe I could do that. I'll see what I do. Maybe for the test next week, I won't include 7.8. And then I can add a couple extra problems from the earlier sections. And then we'll go with the week. Whenever we get that Monday, I was supposed to do 7.6, which maybe I could still do that a little bit, but maybe I'll go over 7.8. So that sounds good. We'll go with that. I can try to have a recording as well, but I think it'd just be better for all of you to not have to worry about watching another one. Also, some of you might see in your test, and I'm pretty sad about this. This happened. Not because of anything you guys did. It's on me completely. And many of you used it, and some of you used it correctly. I still took out points if you didn't use chain rule, because you're supposed to use chain rule always. But on the formula sheet, I wrote this.
Yeah.
And this is incorrect. This is not right. It's supposed to be 1 over x times the natural log of b. So if you wrote that, I didn't take off points. But if you didn't do chain rule still, even with the wrong definition, I still took off a point for that. But I apologize for that. So I'm sorry if you were confused by the derivative there. This is supposed to be the right one. This is not correct. This would be true if this was wrong. But with the derivative there, it's incorrect. So anyway, now that's all my comments. Have a great weekend. Again, watch the 7.7 video. We'll do that. Pay attention to the formulas in that. Sorry if I babble a little bit much in there. There's a lot to explain. Yeah. Yeah. Oh. Was it? Okay, sorry. That needs to.
Oh, okay. Oh, yeah, I just never like update.
Oh, yes, yeah.
Thank you.
Yeah, just you can ignore the 7.8 section for now. It won't be. Yep. I'll just add a couple extra problems for maybe like 7.1 and 7.8. Yep. Thank you. Have a great week. Yeah, you too. Thank you. I have to leave like by now.
All right.
Yeah. I'm really sorry.
Oh, that's fine. I understand.
Yep, you too. Thank you. Absolutely. I hope that there was some enjoyment to be had. It's not as interesting material, so.
Oh, I'm always intrigued.
Great. I'm glad to hear that. Have a great weekend.
You too.
Probably should stop this recording. All of you who are watching this video, if you haven't stopped by now, get this probably see, all this. I'm sitting here leaving this video recording, whatever. All right. Have a great